Very good morning, sir. Am I audible? Good morning, everyone. Welcome to fourth day of the Deep Learning Summer School organized by IIIT Jabalpur. I'm Supriya Sharma and I'll be the session chair for today. I hope you all are enjoying the learning journey so far and finding the sessions insightful. Today's session will be delivered by Dr. Shiv Ram Dubey. It is my great pleasure to introduce Dr. Shiv Ram Dubey, Assistant Professor in the Department of Information Technology at IIIT Allahabad. His interests include deep learning, computer vision, and explainable AI, and he has published extensively in several reputed journals and conferences. He also heads the computer vision and biometrics lab and actively contributes to various academic events and workshops. Sir, we are truly honored to have you with us today. I now request you to kindly take over and begin the session. Thank you very much. Sorry, sir, you're not audible.
Yeah, so thank you very much for the this introduction. I hope I am audible properly and I have shared the screen.
Yes, sir, you are audible.
Yes, yes. So a very good morning to everyone present over here. So in this particular session, we are going to see some of the aspects which is related to the training neural networks, basically optimization techniques. So before moving to the optimization techniques, first of all, we will quickly have a look on a very general classification problem. And also we will see one of the classifier which is very commonly used in deep learning for classification purpose, which is Softmax classifier and using the cross-entropy laws. And then slowly we will build upon the neural network, and then we will see what is perceptron and what is neural network and what is the chain rule in the optimization. And then we will go towards the gradient descent optimization methods, and we will see different optimizers in that case. So if we see in general what is image categorization or classification problem, though this is applicable to any sort of classification problem, image is just one of the application because it is good to visualize. So in image categorization and classification, we have the samples of different categories of the images, and we want to recognize its identity. And basically, in a statistical learning framework, we would like to find out, or we would like to learn a function f. And if we provide our input to that function, then that function should be able to give us the class label of that particular input, which is given to that function. So for that, what usually we do in a statistical learning framework, we divide our data into two parts, which is the training and testing part. So in training part, we say that this is the labeled data set, and because this is supervised learning problem, so we have the training set of labeled examples. Labeled examples means we have the images, means input. We also have its associated class label. For example, suppose if x1 is the first image of apple, then y1 is the class label of that image apple. And similarly, if we have m number of samples in our training set, then we also have n number of class labels for each of those samples. So usually what we want to do, we want to learn a function f such that if we give this input image xi to this function f, then we should be able to predict yi as the output, means its class label. That's what is our motivation to learn this function. And why we want to do that? Because we assume that the test set that we have, the test set will also follow the similar data distribution that training set follows. Then if our model, if our prediction function is able to work well on the training set, then it should also do well on the test set, because the test set examples will also come from the similar distribution of the training set. And in that case, if we have any unseen data x, and if we just give that data as the input to our function f, then our function f will be able to give the output, which is the class label y. That's what is the learning framework. Then the overall problem comes to this particular prediction function f. How to find out this prediction function f such that it should be able to recognize the category of different data samples on in training set accurately. If we are able to do that, then we assume that it should also work well on the test set. For example, we have the neural network, but before neural network, we also have some basic classifiers. For example, suppose if we have linear classifier, and usually we work with multi-class problems, but simpler problem even we can have where we have only two classes. And then we can generalize it for the multiple classes as well. But if we just see a two-class classification problem, which can be one of the simplest problem to solve. For example, if you want to classify cat versus dog, means some samples are there for the cat category, some samples are there for the dog category. And we would like to just find out this prediction function f such that these samples are being categorized into one of the classes. But now if we see here in this particular slide, we are showing some of the data points, and these data points are shown in two different colors, blue and red colors. So what is meaning of that? So a particular data point here is representing one sample. For example, suppose if blue color is denoting the cat category, and red one is denoting the dog category, then one data point here in the blue color is actually representing one sample of the cat. But we have seen cat as an image, then how one sample of the cat is represented here just by one point? So actually, this is not just a point in 2D. This is a vector in some d-dimensional space. So what usually we do, though we have an image, but that image we represent in some d-dimensional feature vector space. So basically, we convert that image into d-dimensional vector, and then that d-dimensional vector is represented here as a point in d-dimensional space. So that's why we are just seeing one point here, but actually this is one sample. So similarly, this red point is representing one sample of the dog category, means one image of the dog category. And what we want to find out here, because this is just a simpler case of the linear classifier. So what we want to find out, can we get a hyperplane here? Because this is in d-dimensional space. So can we get a hyperplane which separate these two distribution? For example, like this. So this one could be one of the hyperplane which can separate these two distributions. Then what is the advantage of doing that? Suppose if we get this hyperplane, if we get the equation of this hyperplane or coefficient of this hyperplane, then our problem will be solved. Why it will be solved? Then for every sample of the cat category, which is the blue one, if we just keep those feature vector values into the equation of this hyperplane, then its output will be negative. And if we consider the red ones, then its output will be positive because it is at the right side and blue one is at the left side. And we know that even in the line also, if we have a point and if we have a line, then we can very easily find out this point is at which side of this line, left side or right side, just by seeing its value is positive or negative. And if the value is exactly zero, then actually that point lies exactly on that line. Similarly here also. But what is the equation of this hyperplane? So we know that equation of a line we can write like a1x1 plus a2x2 plus a3 is equals to 0. That's how we can write equation of a line in 2D. Similarly, if you want to write the equation of a hyperplane in some d-dimensional space, then we can write like a1x1 plus a2x2 plus a3x3 plus a4x4 dot up to adxd plus ad plus 1 is equals to 0. That's how we can write. But usually what happens in case of the machine learning or deep learning, the coefficients are represented using W. So the same thing can be also written as W1x1 plus W2x2 plus W3x3 dot up to WDXT plus WD plus 1 is equals to 0. That's how we can write the equation of a hyperplane in some d-dimensional space. So that can be also represented as a multiplication of the vectors, where we can say that the coefficient of this hyperplane is represented as vector of W. Then what is meaning of this W? So this W actually has D number of values. So this W1, W2, W3 up to WD. So this W has D number of values. And what is X here? X is one of the sample, because sample is also represented in d-dimensional space using a d-dimensional feature vector. So X also has D number of values. Similarly, W is the coefficient of this hyperplane, which also has D number of values. Then we can perform this W dot X. If we perform this W dot X, then actually we are computing exactly same thing that we were computing using the equation of this hyperplane. Because W dot X, if W is a vector from W1 to WD, X is also a vector from X1 to XD, then this W dot X is nothing but W1 into X1 plus W2 into X2 up to WD into XD. This is the same thing. Plus B is basically the bias term here. So what happens now? Now we can get our function f. That function f is now sine of W dot X plus B. This is my function f, where W is basically having the coefficients W1 to WD. B is also the parameter which need to be learned. So what is known here? What is unknown here? X is the data point that is known. W, these are the parameters, are the coefficients of the equation of this hyperplane that we don't know in prior, that we have to figure out what should be the right value of the W, what should be the right value of the B. That's what we need to figure out. Sometimes we can optimize it in a closed form, but many times we cannot optimize this W and B in closed form, means we cannot find out its values using closed form solution. Then we have to go for the approximated solution using stochastic gradient descent. That's what we will see here. But what is the advantage of this function? The advantage is once we know that what is the W and B, then saying that a particular point, a particular data point is at the left side of this hyperplane or right side of the hyperplane is very easy just by seeing the sign of this function. And if sign is negative, then this is the blue one. If the sign is positive, then this is the red one. So it means that we can do the classification like this. But this is a simpler problem with two class. Is it possible to extend it for more than two classes? Yes, we can do that. So suppose if we have three classes, for example, the same thing will happen even we have even C number of classes. So if we have three class, then we consider three classifiers. Then what will happen? This W itself will have now three number of rows. So the first row here of the W, this represents the first class. This is the classifier for the first category. Suppose cat, dog. Suppose third class that we have got here is the SIP. So the first row of W is classifier for the cat category. Second row of the W is the classifier for the dog category. Third row of the W is the classifier for the SIP category. So here we don't take the sign, rather what we do, we find out these scores. We means this is these scores that we get here at the end is nothing but w dot x plus b. So we have dropped the sign term. We only compute the w dot x plus b, and then we try to find out for which particular category we get the highest class score. Then we assume that this input image should belong to that particular category for which we get the highest class score among this cat, dog, and sheep in this case. For bias also, we have the first row of this bias B is for the cat category, second row that is 3.2 here is for the dog category, the third row minus 1.2 is for the sheep category. And this input image X is represented using 4-dimensional feature vector here, Xi. So that's why if we see what is the dimensionality of the W, so dimensionality of the W will be dependent upon what is the dimensionality of the data in which we are representing our samples and what is the number of classes that we have. Suppose if we have 3 number of classes, then W will have 3 number of rows. And if my input image is represented using 4-dimensional feature vector, then W will have 4 number of columns here. So it seems there is some question. Can you explain the parameters in sign W dot x plus b? Okay, so W and B, these are the parameters. So how many number of values in the W? That depends upon what is the dimensionality of X. That is my data. If data has D number of values, if suppose D dimensionality, then W will also have D number of parameters and B will have one parameter. So basically the number of parameter in W dot x plus B depends upon dimensionality of my data, which is X plus 1, which is the bias term. And these parameters need to be learned. How we will learn these parameters? We will use a gradient descent optimization that we will discuss shortly. The input is cat, but the score is high for the dog. Yes, this is possible that happens when our parameters are not correct. In this particular case, our parameters are not correct. Its values are not properly trained. When the values are not properly trained, then it is possible that for any input image, we can get the highest class score for any other class, which is actually misclassification. And that's what is our motivation during training time to reduce this misclassification by fine tuning the values of these W. That's what we will see how it will happen using gradient descent. So another question is how we are converting this image to a vector. So there are several approaches to do that. A simple approach is we have an image, we can just stretch it into a vector. Then suppose if input dimension is d cross d, then input dimension is suppose n cross n, then the number of value will become n squared in my vector. It will become a single vector, but that's not a good idea to use it. We will see in the CNN why it is not a good idea. Other approaches, we can use any feature extractor techniques, which is already, for example, histogram of oriented gradients like HOZ or SIFT or local binary pattern. This type of feature extraction techniques we can utilize to convert image into the feature form. However, nowadays, if we use the CNN, there is need not to extract feature in advance. We can directly give image as the input to the convolutional neural network that we will see in the CNN lecture. W is any arbitrary value. Yeah, initially the values of the W are set randomly, and through training process, we just change this W such that on training set the performance should be very good. Then if on training set performance is very good, then on testing set also it is assumed that the performance should be better. How to choose random weights and bias? So we can choose the random weights and bias. There are weight initialization techniques. For example, there is Xavier weight initialization techniques. There is a Heave weight initialization techniques. These weight initialization techniques are very common. They usually work based on the this randomized means stochasticity. They basically take the values of the weights randomly from zero, mean, and unit. Not unit. This is standard deviation is set based on how many number of neurons we have in the input layer. So for that, you have to look for the weight initialization techniques. Can you explain the use of parameter B? Okay, so the use of parameter B, for example, suppose if you see a line, equation of a line, if you see y is equals to bx plus c, then what is the use of c there? That intercept, basically it gives you the scaling effect. So wherever, even if we see here this just classifier that we have shown here, this hyperparameter. So this hyperparameter, exactly same hyperparameter, we can just scale. If we, suppose instead of having this hyperparameter, this hyperplane here, if the same hyperplane parallelly, if we have here, that will be controlled by B. So how much scaling we can do of the same hyperparameter, that will be controlled by this bias term. Okay, xi and b are different dimensions. So how are we adding these two? Xi and b are of different dimension. Okay, so what happens here? W has dimensionality d, x has dimensionality d. Then we are doing dot product. So w dot x, after dot product, we will get a single value, which is a scalar value. So, and b is also a single value, which is a scalar value. Then we will be able to add these two. Because if we do the dot product of any two vectors, we will get a scalar value, which is a single value. So we can add with the b. So that's how we will be able to do that. How is image converted into vectors? I think we have already and discussed that, answered that image is converted into a vectors. There are several approaches to do that. One, we can simply stretch it out, or we can use some existing feature extraction techniques and convert image into vector form. But if we apply CNN, need not to convert. We can directly give image as the input to the convolutional neural network. Is B is the error correction. B, as we already discussed, using B, we can have the scaling effect in our classifier such that we can have the better generalizability of the models. And even if you are aware with support vector machine, then in support vector machine, we maximize the margin, which is actually very similar to what we are controlling using B here. Why is the score of the cat negative, though it is a cat image? Because W is not correct right now. This W is just a random values. So it is not trained properly. So that's what is our purpose, to train it. How is image converted into vectors? I think same question is already taken. Is there any confusion to anyone? Still, you can feel free to ask. Otherwise, we will move forward. Okay, so here we have seen that's how we can use this linear classifier for more than two classes. Then I suppose if we have three classes, then we actually have to build three classifiers. Why we are doing that? Because similar thing even we have to do in the neural network as well. In neural network also, suppose if we are solving a problem for three class classification, then in the last layer we need to have three number of neurons, and each neuron will provide you the class score for every class. Okay, so now moving forward, in deep learning, one of the classifiers for classification which is very widely adopted is Softmax classifier, and we will quickly have a look over this Softmax classifier. What is that? So the Softmax classifier, it interprets the class score as the unnormalized log probabilities for each class and replace the hinge loss. Hinge loss is actually comes in the support vector machine with cross-entropy loss. Okay, let's try to understand this using example. Then it will be very clear. So what happens here? Suppose we are solving a three-class classification problem, cat, dog, bird, and sheep. And suppose my input image comes from the category number 2, yi is equals to 2. The first row belongs to the first class for which yi is 0. The second row belongs to the second class for which yi is 1. The third row belongs to the third class for which yi is 2. It means that the third row here is the classifier for my class in which I need to classify. And my input data xi is represented here using a four-dimensional vector. At present, these are the values of my parameters w and b. So if I compute the class scores for every class, then class score for cat category comes to minus 2.85, class score for dog category comes to 0.86, class score for sheep category comes to 0.28, and my input example comes from sheep category, for example. Then what the softmax classifier does? Softmax classifier, first of all, projects the class scores into the exponential space. It means that e to the power minus 2.85 is computed here, which is 0.058. E to the power 0.86 is computed, which is 2.36. E to the power 0.28 is 1.32. So these are the class score in exponential space. So then question comes, why to do that? Why to project into the exponential space? Because the class scores, the range of the class scores is from minus infinite to plus infinite. But we need to convert these class scores into the probability. And because there are negative values, then it will create a problem if we convert into the probability. That's why in order to convert all the values into the positive value, we actually use the exponential space. And because negative values are giving the indication that our input image should not get classified to that particular class, because instead of even having correlation, there is a decorrelation with that class. Then in exponential space, those class scores should not be very high. And that's what this exponential function does. Every negative values, when projected into the exponential space, it will be always within 0 and 1, because e to the power minus infinite is 0 and e to the power 0 is 1. So all the negative values will be in between 0 and 1, and all the positive values will be from 1 to positive infinity, 1 to infinity. So that's what will be advantage of using this exponential function. And once we get the exponential function, well, once we get the class score in exponential space, then what we do now? Just do the normalization. How to do the normalization? Find out the sum of these three, means 0.058 plus 2.36 plus 1.32. Find out this sum and divide all these values with that sum. That is actually the normalization. Then after normalization, we got 0.016, 0.631, 0.353. So what is the significance of this? It means that it says that the current input xi, there is a 0.016 probability for this input image to be classified into cat category. There is a 0.631 probability for this input image to be classified into dog category. There is a 0.353 probability for this input image to be classified into SIP category. But during training time, we know that this input image, this input sample has come from the SIP category. Then what we expect? We expect that the probability for classification into the SIP category should be 1. But that is not 1. Right now it is 0.353. It means that whatever classifier values we have of the W, those values are not correct. Then we need to find out the loss. Then that is actually called the error function. That is, and then what is that loss? That loss is computed using cross entropy. And that what that cross entropy does, that cross entropy computes the negative log likelihood of the probability of the correct class. What is the correct class here? Correct class is the SIP category, which is actually the third one. The probability for the correct class here is 0.353. Then what will be the loss? Loss will be minus log of 0.353, which comes to 1.04. Then what we do? Then using stochastic gradient descent, now we will use this, we will use the gradient concept to change the values of W and V. That we will see how to do that. It seems again there is some question here. How are we normalizing? It's very simple. Add all the values and then divide all the values using that summation. What is yi? Yi is the correct class level. What is the correct class level? During training, suppose we know that this is my input and this is the correct class level. If we know the correct class level, then only we can compute the loss. So for example, yi was 2. It means that this is, please explain y is equals to 2. Okay, so these class labels are, in this case, class labels are 0, 1, 2. 0 means the first class cat. If y is equals to 1, then this is a dog. If y is equals to 2, then that is a SIP. And because for the current xi, the current sample xi, yi is 2, it means the current input image is actually belongs to the SIP category. So what we want to do in that case, we want to find out for the SIP category, what is the probability we are getting. Then we know here the probability for the cat category is 0.016 that we got. Probability for dog category, we got 0.631. Probability for SIP category, we got 0.353. And when we compute the cross entropy loss, then we find out the negative log likelihood of the probability of the correct class. And because its y is 2, so its correct class is SIP. And correct class probability is 0.353. That's why we take the minus log of 0.353. And that comes to 1.04, which is actually the loss here. I hope this is clear now. Was it assumed that SIP is the correct target level here? Yes, it is assumed that it is the correct target because we assume that it comes from the training data. And we know that correct category is SIP, for example. How to compute cross entropy? Cross entropy is computed as minus log of probability of the correct class. And in this case, correct class is SIP, which is actually the third one. So that's why we take the minus log of 0.353. If we have two classes with same probability, then we will find loss for both or not. We find loss only for the correct class because at the training time, we already know that for my input sample, what is the correct class. Then whatever is the probability for the correct class, we take the minus log of that. So shape of W should be shape of Xi. No, shape of W should not be shape of Xi. The number of columns in W should be same as the shape of Xi. But the number of rows in W depends upon how many number of classes we have in my data set. For example, suppose if I had 10 number of classes and Xi has 100 values, then in that case, my W will have 10 number of rows and 100 number of columns. Yi equals to 2, which means our prediction should also give maximum probability for SIP, which was not the case initially. Hence, we calculated loss using cross entropy. Yes, exactly, you are correct. And then our aim is to minimize this loss. And in order to minimize this loss, we will change the values of W and B such that next time this loss should go down by making the probability for the correct class higher. The highest probability is the predicted class. Yes, during testing time, whatever is the highest probability, that will be the predicted class. But during training time, whatever is the probability of the correct class, that we will use to compute the loss. How did we get minus 2.85? Minus 2.85 we have got by, if we take the first row of W and do the dot product with Xi, means 0.01 into minus 15 plus minus 0.05 into 22 plus 0.1 minus into minus 44 plus 0.05 into 56. This is the dot product of the first row of W with Xi plus the V values of the corresponding row, which is 0.0. That will give us minus 2.85. If we repeat the same process with the second row of the W and second row of V, then we will get 0.86. That's how we compute the class score. What does 1.04 represent? 1.04 represent the loss. What is the loss for this particular input? But sir, should we not find log of all three classes and sum the loss? Actually, we are doing the same thing. So what happens in cross entropy loss? We are finding the log of all these three terms, but when we are multiplying, then we are multiplying 0 point minus log of 0.016, we are multiplying with 0, and minus log of 0.631, we are multiplying with 0, and minus log of 0.353, we are multiplying with 1. Why we are doing that? Because the current input belongs to the third class. Fine, that is for that yi is 2. So what happens actually, class label is represented as a one hot vector. What is meaning of one hot vector? Suppose if I have three classes, then class label will be represented as a binary pattern having 0 and 1, and all values will be 0, only one will be there, which is actually corresponding to the correct class. So what happens if yi is 2, then actually one hot vector of the class label is 0, 0, 1. So in cross entropy, we actually compute 0 into minus log of 0.016 plus 0 into minus log of 0.631 plus 1 into minus log of 0.353. But for except the correct class, for all other classes, because this one hot encoding vector having value 0, then what happens? It is always getting 0. So that's why I need not to compute it. I hope that should be clear. Is our objective to have weights ST? This cross entropy becomes 0 from greater than 1 now. The cross entropy loss will become 0 only if the probability for the correct class becomes 1, which is in practical, that is not possible to perform. But hypothetically, yes, that is possible. We can get the probability 1, then loss will become 0. But in practice, usually it doesn't happen because it is very difficult to have the class score minus infinite for all other classes and towards positive infinite for the correct class. So in practice, that's very difficult to achieve. How did we get minus 2.85? We have already explained it. That is taking the different rows of this W, performing dot product with xi, and then adding the v value. Please repeat normalization. Normalization is nothing but whatever values we have, add all those values, and then divide these values with that summation. That is the normalization. If we have same rows for W and X, then can we use transpose of W and X? No, that is not correct. Because the row of W represents for different classes and columns represent different data dimension. So we cannot transpose the classes with the dimension, then it will become wrong. It is hot encoded. Yes, that is one hot encoding for class labels. Here we have used the software definition of cross entropy. What could be other ways, if any? That's what I just discussed. The cross entropy means because we are getting this entropy from the final class probabilities that we have, and we take the this class labels in one hot encoding. So that's why this is cross entropy here. This is supervised learning, and third is the target. So it should be sigma of negative log. No, there is no sigma here. This is just negative log likelihood. So sigma is a different thing. Sigma is sigmoid, which is actually used for a different purpose. When we want to have the logistic regression, then we can use the sigma there. Each row of weight matrix is a weight vector associated with each class. Yes. So first row of the weight matrix W is for the first color class, second row is for the second class, third row is for the third class. For error minimization, can we update only one parameter, weight or bias, or proceed, or do we need to update both? We need to update both because what happens here at the end, the class scores that we are getting, it depends upon both W and V. So we need to update all the parameters. Okay, so yeah, now let's move forward if there is no further question. So that's how we can use this softmax classifier and cross entropy laws. Then for any parametric model where we have the W's, we have the input, we have the bias, we can get the class scores. Those class scores are converted, means we can take the e to the power of that, then normalize it to convert into the probability, and then take minus log of the probability of the correct class as the error function. And based on that, we have to perform the optimization of this W and V using gradient descent that we will see shortly. So now when problem comes, so this problem is very easy to solve if it is linearly separable. Now what is meaning of linearly separable? If the samples which comes from one category and samples which come from the other category, if there is a clear-cut separation between these two, and if we can have an hyperplane to divide these two distributions, then it is very easy to solve. That is called the linearly separable problem. But what happens? Suppose if some of the blue points are at the right side also and some of the red points are at the left side also, then problem becomes difficult. Then in that case, we cannot have a hyperplane which can clearly separate these two distributions. And then we cannot have a linear classifier which can solve this problem. Then what we can do means for the complex problem where our data when our data is not linearly separable, when they are very mixed with each other, then in that particular case, there are two major approaches. One is called the shallow approach, means somehow now we have to bring the non-linearity in the system. So because using linear classifier, now that problem cannot be solved accurately. So one approach is shallow approach. In shallow approach, what we do, then we project our input data itself using some non-linear feature transformation such that in transformed feature space, it should become linearly separable. And if it becomes linearly separable in the transformed space, then we can have a linear classifier on top of that to perform the classification. This is one shallow approach, which was usually being done before deep learning came. But after deep learning came, then we got the deep approach. And in deep approach, what we do, we have the stack of multiple layers of these linear predictors, but these are separated by the non-linearities. So non-linearities, there are some non-linear functions, which is also called the activation functions in deep learning term. And what we do there, basically using those non-linear functions, our input data itself is getting projected into the feature space in an hierarchical fashion and in non-linear fashion, such that at the end, when the final classifier is going to be applied at the last layer, before that, whatever is the representation of the input, that will become linearly separable, or it is more towards linear separability as compared to the original data. So these are two approaches. So shallow approach, which was being done earlier, this is just one example to understand how this shallow approach works. So here we can see, if we see the left side, we have the blue colors and red colors. Now it is not possible here to have a linear hyperplane to divide these two distribution exactly. That's not possible in this case. Then what we do? Suppose if we project this data itself into some other space, means some higher order space here. For example, this original data was represented in two-dimensional space, but if we project it into three-dimensional space here, so after projecting into three-dimensional space, what has been done? All the red ones has gone towards the basically this downside here, and blue ones are there at the upside by making use of one additional dimensionality. And now here we can see in this three-dimensional space, we can have a hyperplane. We can have a plane here which can clearly separate these two distribution. So this is basically the shallow approach. But what is the disadvantage of the shallow approach? The disadvantage is then what should be this transformation function that we don't know. Here we are able to visualize because this is represented in this two-dimensional space and three-dimensional space. But suppose if my data is represented in 1,000-dimensional space, then it is very difficult. We cannot visualize even that. Then how to find out what should be the right transformation function which can convert my data in some higher order space where it is linearly separable is very difficult task. So that's why nowadays we have the multi-layer neural network to solve this problem, where we have the multiple layers, and in between we have multiple non-linear layers, and those input data will be projected into feature space where it will become linearly separable in a hierarchical fashion. And also there are multiple other aspects that we will see shortly. And that is referred as the deep approach. So there is a question here. Someone starting to work in deep learning can start straight with neural network, or one needs to learn ML first, like SBM or other ML algo or other fundamentals. Okay, getting to know machine learning fundamentals is very, very essential if you want to understand deep learning very well, because the deep learning is kind of an extension of machine learning. So that's where you should know the basic concepts of machine learning while you are going to the deep learning. If you don't know, still you will understand something, but then it will take just time to grasp the concept directly if you are going into the deep learning. But if you already know how this classifier works, how support vector machine works, how this k-means works, if you're already knowing all these things, then it will be easier to you. So there is one more question here. Is shallow approach using support vector machine? Shallow approach, even we can use neural network also in shallow approach. Shallow approach means we extract the feature from our input using some hand designed approach, using some manual approach, and then using that extracted feature with any of the classifiers. Either it can be linear classifier, or it can be support vector machine, or it can be neural network. It can be anything on top of that. However, in deep approach, the extraction of the feature is not done manually. Rather, we have the parametric approach where the extraction of the feature directly done by the neural network itself. And we have non-linear data activation function help in deep approach. Yes, this deep approach will help. How in deep approach, linear plus non-linear will give a new dimension. Okay, that you will understand once you will understand the concept of neural network and convolutional neural network, because there in CNN we have the concept of these different filters that is also called the kernels. So having these different kernels can have a different dimension. So after going after the neural network and CNN concept, you will better get to know about this. So there is another question. Can you please state the difference between parameter and features? Okay, very good question. So what is parameter? W is the parameter. What is the feature? Xi is actually the feature in this case. So when we are doing W dot X plus B, W and B both are the parameters and X is the feature. So this is the difference between parameter and feature. Even in neural network at different stages also, we perform the same task, W dot X plus B. Everywhere in entire deep learning, W dot X plus B is being performed. Either it is linear classifier or neural network or convolutional neural network, or even if you go to nowadays, this large language models, everywhere we perform W dot X plus B. There is another question here. The shallow approach is like one big single block of non-linearity and linearity, unlike deep approach, which is divided into many small blocks of linear plus non-linear. Yes, exactly same. And that's why it is helpful here. So yeah, now let's proceed further because we have limited time uh, such that you can better correlate the things with the optimization. Okay, so now moving forward, we have the concept of neural network. So the concept of neural network is actually derived from the perceptron. And what is the perceptron? Perceptron is exactly same thing that we have seen in the linear classifier. What we have done in linear classifier, we have the hyperplane. Equation of that hyperplane is represented as W dot X plus B. The same thing is also represented in the perceptron, but it is just represented in the form of a computational graph. So what happens? We consider this circle here as a tiny computational unit which receives the input x. This x is having d-dimensionality, so x1, x2, x3 up to xd. And then we say that each of these connections have the parameters or the weights, which is represented as w1, w2, w3 up to wd. And what we have some non-linear function, like we can have the sine function, we can have the sigmoid function, we can have any nonlinear function here on top of that. And what we perform, basically we perform the same task, x1 in dot x1 into w1 plus x2 into w2 plus x3 into w3 dot 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 plus xd into wd. Whatever we get in that, we add the bias term. Bias is not shown here, but we can have the bias term also. And whatever we get on top of that, we apply this non-linear function z here, and then its output is the final output of this perceptron. So then what could be this non-linear function? So if you see when this neural network was started long back, then sigmoid was one of the by default this non-linear function that people were using, though it has some drawback. But why sigmoid was being used? Because the output of sigmoid is always between 0 and 1. So what happens? It was actually inspired from the biological neuron concept, because in the biological neuron, what happens? A particular neuron performs some task, and then it basically fires the signal. And when it fires the signal, then it fires in between the strength of 0 and 1. So from that particular perspective, this is derived. And then sigmoid was one of the function which converts any input between 0 and 1. But later on, it figures out that this sigmoid is not a very good activation function. And nowadays, ReLU is one of the popular activation function that you will come to know in different session where activation functions are discussed. Okay, so now using this perceptron, basically we can also refer as the neuron. We can have a neural network. So in neural network, now we can have the multiple neurons, and we combine the multiple neurons in a particular fashion such that we can basically have a neural network. So here, if you see, this is a neural network with two layers. Okay, but here you can see there are three layers, but I am saying two layers. Why? Because the first layer is input layer, means first layer is the input itself, which is not counted as the parametric layer because there is no parameter here. These are only the input values that we are providing. So it is the input layer is not counted actually as a layer of the neural network. Then where is the layer? The output layer is one of the layer and hidden layer is one of the layer. So now if you see in this particular example, how many number of neurons we have? So we have in this example, one neuron in the output layer and five neurons we have in the hidden layer. So total number of neurons in this particular example is six. Five in the hidden layer and one in the output layer. There is no neuron in the input layer. These are input values. So what happens? Every neuron, if you take every neuron in the hidden layer, then it receives input from all the input layers, means all the dimensionality of the input that we have. In this case, my input is represented as a 4-dimensional vector because we are having these 4 values which are being shown in the input layer. So all these 4 values will be provided as the input to every neurons in this hidden layer. And every neuron of this hidden layer will have its own bias term also. And every connection here will have the parameters or the weights. And every neuron in this case will have their own set of parameters. So how many number of parameters will be there for the first neuron in the hidden layer? That depends upon how many number of inputs it receives. For example, if it receives 4 inputs, then there will be 4 parameters, W1, W2, W3, W4, because we need to perform dot product and one bias term. So 5 parameters will be there with the first any of the neuron in this hidden layer. Similarly, if you take the output layer, then the output of every neurons in the hidden layer will serve as the input to the output layer neuron. So for example, here we have a single neuron in the output layer. Then in that case, we wanted to predict some output. So for example, suppose we want to predict the age of a person, then we need only one neuron in the output layer because we need a single output in single as the final output. But suppose if I want to do the classification into 3 classes, then output layer will have 3 neurons in that case. And every neuron will receive exactly same input, which is the output of the hidden layer. So, and all these hidden layer neurons will also have their activation functions, which is Z, that is the nonlinearity. And output layer will also have its own nonlinearity. So the final output here is represented as, for example, this W1X represents the output of this hidden layer combined, which is given as the input to this output layer neuron. And then we have the parameters here in the output layer neuron itself, which is the W2. Then in that particular case, that parameter is also applied here, and activation function of the output layer is also applied. Then in that case, whatever we get the final output here, this is going to be the final output of this particular neural network in this case. Okay, so there is one question here. Thank you for clear and patient explanations to our queries. Could you please explain what is the essential difference between a perceptron and a linear classifier? Okay, so what happens in a linear classifier, we take the sign of W dot X plus B if we have a linear classifier for 2 classes. But in the perceptron, we do not take the sign, rather we take any non-linear function. That non-linear function could be sigmoid. If you see the original perceptron, then sigmoid is used because then sigmoid is converting its output between 0 and 1. Then it can be also considered as the probability, because if any output is between 0 and 1, then that can be treated as the probability for any particular problem. Sign means what? Sign means positive, negative. So if we take sign of W dot X plus B, if W dot X plus B is negative, then its sign is basically the negative. If that number is positive, sign is positive. If sign is negative, then we say it belongs to the category 1. If sign is positive, then we say it belongs to category number 2. But the sign function works only if we are having 2-class problem in linear classifier. But if we have more than 2 classes, then we compute the classes scores, and finally we use the softmax classifier, get the probabilities, and then from the probability score we do the classification, that for which class we get the highest probability. In that class, that input will classify it. Okay, so now let's move forward. We have seen this just a two-layer neural network. Now one question is here, what is the significance of the number of neurons? For example, here in this case, the total number of neurons we have is 6, 5 in the hidden layer, 1 in the output layer. So we have total 6 number of neurons. Then what is the significance of the neurons? So here we can see 3 scenarios. In the first scenario, we have 3 neurons. In the second scenario, we have 6 neurons. And in the third scenario, we have 20 neurons. And we can see here, and we also have the data points. So red one is from one category and green ones is from some other category. And what we are showing here is the decision boundary, which is learned by our neural network. So when we have 3 hidden neurons, then the decision boundary which is learned you can see decision boundary in all these three cases are non-linear. Why non-linear? Because we have neural network, we have non-linearity layers there. So the decision boundary is not linear, but non-linear. If you see the linear classifier where I showed the hyperplane, that was also a decision boundary, but that decision boundary was linear decision boundary. Now here, this is non-linear decision boundary. So now in when we have three number of neurons, still we can see some of the red points are not being captured into the decision boundary of the red class. Why? Because the learning capability of the neural network with only three hidden neurons is still limited as compared to if we have six number of hidden neurons. So we can see when we have six number of hidden neurons, then this particular red point is also considered very well in the red island, because now we can even learn more complex nonlinear decision boundary. And when we have 20 hidden neurons, then even we can learn even more complex decision boundary. So even if we have a very complex problem means their data distribution is very much overlapped with each other for different classes. Then in that case also, if we have a large number of neurons, then our model will be able to learn in such a way that it can basically have the complex decision boundaries learned. And also there is a theorem which says that if any neural network having a hidden layer with infinite number of neurons in that hidden layer can learn any complex function which can exist. Any complex function which can exist can be approximated by a neural network with only one hidden layer. But given that, we should be able to deal with even infinite number of neurons there. Okay, what is softmax? There is a question here. What is softmax function? Softmax function, when we got the class score, we have taken e to the power of that, fine, and then after that we have performed the normalization. That is actually the softmax function. On top of that, when we computed minus log of the probability of the correct class, that was the cross-entropy loss. So the role of the softmax function is to take the class score, convert into the probability. That is actually the softmax. The same thing can be also written into the equation form. Another question is how to decide number of neurons in hidden layer. So there is no hard and fast rule here how to decide. That actually comes through the practice. When you solve the problems, when you have different type of problems, different type of neural networks, when you are developing, and then from your experience, slowly you will be able to get this idea that what should be the number of neurons in the hidden layers. That depends upon what is the complexity of your problem. If your problem is very simple, then less number of neurons will be required. But if your problem is very difficult, complex problem, then more number of neurons would be required. That slowly you will understand. So you have taken a neural network, suppose with 100 neurons, you are getting underfitting or overfitting. Based on that, you can have even with a less neuron or with more neuron that can be decided. How to decide hidden neuron? Like for 40 neurons, it will make a better. Yeah, that's what we just discussed. That depends upon complexity of the problem. What a three-layer neural network will contain. So a three-layer neural network, I will just come to that. A three-layer neural network will have basically multiple hidden layers into just you can see here. This is a neural network with three layers. This is beyond two layers. In this case, we have two hidden layers. The input is given to the first hidden layer. The output of first hidden layer will serve as the input to the second hidden layer. And output of the second hidden layer now will serve as the input to the final output layer. Similarly, suppose if someone has 10 layers, then in 10 layers, you will have 9 hidden layers and one output layer. And here output of hidden layer 1 will be treated as input for hidden layer 2. Output of hidden layer 2 will be treated as input to hidden layer 3, like that. And that's what was the deep pipeline, if you remember. Layer 1, layer 2, layer 3. And because if all these neurons also has a non-linearity, so hidden layer 1, we perform w dot x plus b, then have given to the non-linear function. Its output is given as the input to hidden layer 2. Again, we perform w dot x plus b, but those parameters will be different now. And then this output will be again given to the non-linear function. That output is given as the input to the output layer. That's how basically we have this hierarchy of these hidden layers in this case. Okay, there is one more question here. Can you please discuss about the final outcome in the linear classifier and in a perceptron? The final output layer is giving a final answer or a boundary. Okay, the final output layer will not give you the boundary. The final output layer will give you the final output. For example, suppose if my problem is to predict the age of a person, then this output layer will give me a scalar value, which will be the age. That is going to be the output here. Suppose if my problem is classification in three classes, then I will have three number of neurons here, and those three neurons will give me the class score for class 1, class 2, class 3, and then from those class score we can find out for which class we got the highest class score, and then classification will happen to that class. Now if you are getting confused with this figure, with this decision boundary, how we got this decision boundary, so what we have done in this case, so if you see every input here means every place is considered as the input and given as the input to the neural network, and based on that we are finding in which class it is belonging, and then we are just plotting this. So this decision boundary is not directly given by the neural network to you. This decision boundary we are interpreting from the data distribution, that if my data was basically placed here, then in which class it got classified. So based on that, I will come to know that if this particular sample is classified in this class, then obviously my decision boundary should be like this. Okay, so there is another question. In hidden layer, only the w dot x plus b is happening and the activation function is only in the last output layer. No, activation function is there in every hidden layer also. So in every layer we perform w dot x plus b followed by the nonlinear and then giving that one as the input to the next layer. How to choose 3 input layer, 6 hidden layer like this? Okay, so that again depends upon the complexity of the problem that you are solving. If you have a very complex problem, then even we can have more number of layers. And if we have more number of layers, then we can also manage with more number of neurons. So that depends entirely upon the complexity of the problem that we are solving. Why we have multiple hidden layer can be only, so there is another question. Why we have multiple hidden layer? Can we have only one layer not enough to achieve the desired result? Very good question. Yes, as I already mentioned here, any problem can be solved using a neural network having only one hidden layer. But what is the problem? The problem is if you are having a complex problem to be solved, then the number of neurons in that hidden layer might be required is close to infinite. Suppose if you require to have the 10 million number of neurons just in one layer itself. And what happens because we perform w dot x plus b, then in that, and for every neuron we have to perform this w dot x plus b. And if we are having suppose 10 million number of neurons in one hidden layer, then how much computation is required? So though we can use it, but computationally it will become very, very expensive. And even it is also possible that we might not be able to afford that. But if the same thing is converted into the multiple in a hierarchical fashion, then it is possible that even using less number of neurons, we just transform the our data into some feature space, and then we further transform, then we further transform, then we further transform. If we transform it multiple times, then it is going to be helpful. Why it is going to be helpful? If you have only one hidden layer, then your non-linearity is being applied only once. But if you are having suppose 10 layers, then your non-linearity is being applied 10 times. Then what happens? Something if we are non-linearity, if we are repeating 10 times, then we can have the better non-linear transformation as compared to transforming only once using the same non-linear function. Because our non-linear function is same. If you are applying only once, then we need large number of neurons, and it will become infeasible to solve the complex problem. Some easy problems can be solved using one hidden layer also. Complex problem if we have to solve, then we have to rely on several number of neurons, and then it will become computationally expensive, and we cannot basically do that. That is the problem. That's why we have the hierarchical. We have 10 layers, 20 layers, 30 layers, such that nonlinear function is being applied multiple times, such that overall even using less number of neurons, we should be able to get the desired level of non-linearity introduced into this entire transformation. Okay, I hope that you got some clarity. There is another question. Sigmoid resembles biological neurons. So is it similar to spiking neural networks? Yes, some sort of, you can just think of that. For image, how to choose the input and hidden layer? That depends upon the complexity again. Uh, when we will discuss the convolutional neural network, then you will get better picture of this image. So there is another question. What will effect of time? Will time take be more on increasing the number of neurons? Obviously, if you increase the number of neurons, then for every neuron we need to perform W dot X plus B. For every neuron we have to apply the nonlinear function. Then it will take more time. Our time would be more when hidden layers is increased. Okay, when we have only one layer but large number of neurons, then time complexity will be more there. If you want to match with the similar accuracy with more number of neurons, more number of layers, but with less number of neurons, then in that case, even with less number of time, with less number of neurons, we can get the similar level of accuracy. Keeping total number of perceptrons same. If your number of neurons is same in both the cases, then which one will take more time? Then having more number of layers will take more time, because in that case you're going because in that case you are going to pass the input to the output of one layer to as the input to the next layer, and you are going to do that particular task but multiple times. But if you are doing only once, then using GPU, you can do the parallel processing, and in one go you can compute if you have only one hidden layer. But suppose if you have 10 hidden layer, then you cannot parallelly process all the 10 hidden layers, because the output of hidden layer 1 is going to serve as the input to hidden layer 2. So without processing hidden layer 1, hidden layer 2 cannot be processed. So there it will take more time. There is another question, how to decide the amount of non-linearity to be added after every layer. Okay, this is a very complex problem that we cannot decide by ourselves, that network will decide automatically. What we can do, we can just add the nonlinear function with every neuron. Which nonlinear function to add? For that, there are several rules. For that, there is several pros and this downside of different nonlinear functions. And then it turns out that one of the activation function like ReLU that works better in practice. That is a completely different subject that can be discussed in the activation function topic. Okay, so now let's move forward. So we can have this type of deep pipeline where we can have the multiple layers here, like these hidden layers, and our input is being transformed by hidden layer 1, then hidden layer 2, then hidden layer 3, like that. And at the end, we have the final layer, and the final layer will get the number of neurons in the final layer. That depends upon what problem we are solving. Suppose if we are doing like age prediction, only one neuron is required. If you want to do the binary classification, only one neuron is required. But if you want to classify in 10 different classes, then 10 number of neurons are required. So that depends upon the problem that we are solving. Okay, so what is a very important question here, and the topic that we are discussing, there is one question. Multiple hidden layer helps in finding complex patterns. Like one hidden layer gives a straight line, but as we go on increasing the hidden layers, more complex structure helps in classifying the data for us. Yes, that is true, because when you combine this non-linear function multiple times, then the decision boundary that we learned becomes more and more complex. Okay, there is one demo I will show in the demo, then you will have a better clarity. Okay, I can just directly go to that demo. Let's see if it is there. Yes. Okay, let me directly go to this demo, then some of your queries will be automatically resolved. I hope this is visible because I'm showing in the browser right now. So here you can see this is basically just a neural net. We can build a neural network here and perform the training, and we can visualize the loss plot. We can visualize the decision boundary using this portal. So what does decision boundary mean? That you will see in this particular demo here. What is the decision boundary? So now if you see here, what we can do here, we can build a neural network. At present, we have two hidden layers. We can see this is the first hidden layer where we have 4 neurons. We can, if we want, we can reduce them. For example, I just reduced to 3 neurons. And this one is having 2 neurons. This is the second hidden layer, and this is the output layer. Even I can add the number of hidden layers. For example, if I add one more hidden layer, so now we have 3 hidden layers. Suppose if I increase, here I have increased to 5 neurons. In this case, suppose I increase to 4 neurons. This is 6 neurons. This one also I can suppose I increase to 4 neurons. Now, if you see, this is a neural network with 3 hidden layers. The first hidden layer has 4 neurons, second hidden layer has 6 neurons, the third hidden layer has 4 neurons. The last layer, the problem that we are solving is this is a classification problem. We have the binary data. So basically, the last layer have only 1 neuron, and its output on the output word activation functions that we are treating right now, tanh. So even suppose if we have the sigmoid activation functions with sigmoid nonlinearity. And this is the data set here. We can see the data set is not linearly separable. It is non-linearly separable data. And we can see here. Now at the right side, you can see this is the data distribution. And if I'm going to start the training here, learning rate is set to 0.003. I will talk about learning rate right now. Means after this demo, I will tell what is meaning of that. Regularization is a different topic that we'll discuss later on. Right now, we are not using any regularization. This is a classification problem. So what is meaning of classification problem? The red ones should be classified into the red category. The blue ones should get classified into the blue category. And if I'm going to start the training, and the ratio of training to test data, so 50% of the data is used for the training purpose. Even let's increase that. Suppose I'm going to use 70% of the data for the training purpose. There is no noise right now. Batch size is set to 10. Batch size is a different thing that we will see shortly after some time. So now if I start the training here, so training happens in the iterations. I will tell that in after some time. But here we can see what is the training loss. The training loss is showing 0.5. Fine, and we can see this training loss is 0.5, and nothing is happening here. We are not getting any proper decision boundary. And why this is happening? Because sigmoid activation function is not a good activation function. That is not a good nonlinear function. Why? Because there is a saturation problem there. When you will study the activation function, then you will come to know that there is a saturation problem. Due to that, this is not a good activation function. But after training for many number of iterations, now training loss is slowly decreasing. Now it has gone to 0.493, and now it is further decreasing. And while this loss is decreasing, you can see here this decision boundary is coming. Now this is the decision boundary. So what is meaning of this decision boundary? Everything which is within the decision boundary, means at one side of the decision boundary, is actually being classified into the one blue category, and which is at the other side of the decision boundary is being classified into the red category. Now we can see what is the training loss. The training loss has gone to 0.001. So you can see this is the impact of training the neural network with the sigmoid activation function. Now let's try to understand the difference between the sigmoid and ReLU. Suppose instead of sigmoid, if I'm going to use the ReLU activation function, which is called the rectified linear unit, and if I'm going to use the exactly same setup and train it again. So now here you see what was the difference? Very quick. Again, let's change it to 10. Let's change it to the ReLU again. Now, what we have seen in case of the sigmoid, it has taken more than 1,000 number of epochs, means the in terms of iterations, even to figure out what is the right decision boundary. But when I'm going to train with the ReLU activation function, it takes even hardly 10 to 20 epochs to figure out what is the right decision boundary. And you see the training loss is 0.000. It is not exactly zero. Still, if you go into some higher precision, then there is a loss, but it is not exactly zero. But what happens here? Now, if you see this decision boundary, if you see of this ReLU activation function, and if you remember the decision boundary when we have seen the sigmoid decision boundary was much smoother, but the ReLU decision boundary is Like this is pieces of the line here. This is one line, this is another line, this is another line, this is another line, this is another line, another line. This is kind of a combination of the lines. Yes, that is true. Why? Because ReLU activation function itself is a linear function, which is 1 for every positive value and 0 for every negative value. So that is a linear function. And when we have the multiple neurons and multiple hidden layers, then in that case, what happens? Those linear functions are getting combined to get basically a decision boundary, which is combination of these linear functions. And at the finally, it becomes non-linear because this is a combination of the linear function and also shifted. So now you can see what was the role of B there. The role of B is basically the shift, because even if we have a linear function, we need to shift and even we need to rotate all these things that we have to perform that is actually controlled by these parameters. So, and also suppose if someone does not use any nonlinear function. For example, if there is no nonlinear function, all the neurons are without any nonlinear function, means w dot x plus b without passing to any nonlinear function directly give as the input to next layer. Then what happens? So in that case, if we do not have a nonlinear function, then decision boundary cannot be nonlinear. Then decision boundary will be always linear, like a hyperplane, like a line. And if we have such a decision boundary, then this type of problem cannot be solved. And here we can see, suppose if I perform the training without any non-linearity, so you can see the training loss is 0.498. And you can also find out the decision boundary here. The upper side is having a different color, downside is having a different color, but only there is a shift in the color. But we cannot find out any non-linearity. We are only having the linearity. There is no non-linearity. Now, even if you train for infinite number of iterations, still your model will not be able to train because there is no scope here for the training. We do not have any non-linearity, then our model cannot figure out any non-linear decision boundary. That's not possible. That's why it is very important to have the non-linear function. Okay, so let's do one more thing. Suppose if I remove the hidden layer, suppose if I have only one hidden layer with 4 number of neurons, and if I'm going to use the ReLU activation function again, and if I'm going to train it. Now here you can see it has taken more number of epochs to figure out what is the this decision boundary as compared to when we had more number of neurons. Even what I'm going to do, let's suppose I have reduced the number of neurons also, only one hidden layer and only 2 neurons. And if I'm going to train it, now you can see what is happening. This is very interesting, right? So here you can see it is very difficult now for my neural network to find out the exact nonlinear. There is a nonlinearity here, but amount of nonlinearity is less now in this case. And now it is very hard for my neural network to figure out the exact nonlinear decision boundary. Because why it is happening? Because the non-linear this non-linearity that we are applying, we are applying only on these 2 neurons. It means that the rectification, we are able to do the rectification only 2 times here. That's why we can see 1 times rectification gives us this upper part here, another side gives another rectification gives the down one. And even we can also do one more thing. Suppose if I have only 1 neuron in the hidden layer, then what happens? If I have only 1 neuron, it means only 1 time we are doing rectification. So we can see the decision boundary that we are getting here, this decision boundary is kind of a linear decision boundary. Why it is a linear decision boundary? Because we have only one nonlinear function right now, which passes all the positive as it is and just converts all the negative into 0. So what happens? Actually, we are having a linear function, only the negative is converted into 0. And because we do not have multiple nonlinear functions, so we do not get its combined effect. So it is equivalent of this linear decision boundary. But if we go with the 3 number of neurons, then we can see now we are able to get this nonlinear decision boundary. But if you see if you see in this nonlinear decision boundary also, this is just combination of 4 lines. Why it is combination of 4 lines? Because we actually have only 3 number of nonlinearity here, and if we also consider the one output layer, so only 4 number of these rectifications we have. So the linear decision boundary that we had, only 4 times it can be rectified. It means only 4 times it can be changed. That's what is happening. If the linear function, if we are changing only 4 times here, then we are getting this type of non-linearity. So that's what is the effect of number of neurons. Suppose if I go with 4 number of neurons, now we can see the how many number of times this rectification we do. 1, 2, 3, 4, 5, 6. Roughly 6 number of times we are getting. Why? Because we have hierarchy also. Due to hierarchy, we get the multiple combinations. So that's why we are able to get this type of decision boundary. But suppose even with the only 2 number of neurons, let's do one more thing. I have only 2 neurons, but suppose I am going to have 6 number of hidden neurons, and every neuron has every hidden layers have only 2 neurons. Then in that case, if I am going to train it, then what is going to happen? Now, if you see, the training loss is 0.5, and we are not able to learn anything. So now what is happening here? So actually, this is a problem that is called the optimization problem, and that is actually related to the gradient diminishing problem. Because we are going to do the optimization, we have to back propagate the gradient, and when we have the multiple hidden layers and we have the ReLU activation functions, then there is a problem which is called the dying ReLU problem or gradient diminishing problem, because ReLU converts the negative values into 0. And here we can see after some number of training epochs, some losses decrease, but still. Now, if we train it for very long time, then we will be able to basically get the final output. Even the training loss will be very less, but we have to train for very large number of iteration in that particular case. So this particular problem we will see later on. That is called basically the gradient diminishing problem. That's why we have different optimization techniques. So now, if you have any questions, there are some questions here. We have to add the bias term to shift the linear outputs, right? So yes, bias term will give you the shifting effect, scaling effect. Why is ReLU so efficient than sigmoid? Because sigmoid has the saturation problem. Its gradient is basically diminished. Because if you see in the sigmoid, when your negative values and positive values, it's kind of a horizontal. When it is horizontal, then gradient is 0, because entire optimization is based on the gradient. If gradient itself is 0, it cannot learn quickly. That's why it takes more time. What is the difference between test loss and training loss? So training loss is computed on the data which is part of the training set, and test loss is computed on that data which is part of the test set, because we divide our training data also into training and test part. Is it necessary to construct a fully connected perceptron or layer? Yes, if you are having a neural network, it is always fully connected. All these computations are time dependent, independent, and only do computations on the data values. So what will happen in case of time series data? Yes, time series data. For that, we have the different variant of neural network, which is called recurrent neural network. And if you have time varying data, then we can use a recurrent neural network, which makes use of the same network, but on data at different time stamp to perform the computation. Why the features are some kind of functions in the simulator? Yes, it is always functions, because whatever we are doing, we are any task we are performing, that can be written as a function. And what function we are doing here is w dot x plus b. That is my function. On top of that, we have the nonlinear function. Neural networks can only do supervised learning, right, sir? No, that's not correct. Even unsupervised learning problem also we can solve. What is required for neural network is to have a right loss function. That, for example, cross-entropy loss we got for the supervised problem classification. For unsupervised problem also, if we can get a loss function, then we can even solve an unsupervised problem using neural network as well. And in fact, already there is a network like that's called autoencoder, which is also built using neural network that basically performs in unsupervised setting. In this, there is another question. In this TensorFlow example, what is x1 and x2? x1 and x2, these are two different dimensionality of my data. My input data is represented using two-dimensional vector, which is x1 and x2. Is it tabular data set and gives a spiral output finally? No, this is different dimensionality of my data. Okay, so from this demo, I hope that you might have got some idea. But again, let's come back to this optimization part. Now we will slowly go into the optimization. So what is very important to understand here is what we have assumed so far. What we have assumed so far that the parameters the W and B, we are assuming that if it is known, then what we can do, fine. But the problem is if we are having a particular data set, if we have a problem to solve, then this W and B, these parameters are not known in prior. When it is not known in prior, then using training set, we have to perform the training to find out the right value of the W. So what is the approach that we generally follow is based on the gradient, which is called following the gradient approach. That is the strategy 3 here. So what is gradient? And that is called the gradient descent approach. What we do in gradient descent, we find out we find out the W to minimize the loss. For example, we have computed the cross-entropy loss. What we want to change the parameters, means we want to change the values of the W such that next time the loss should get decreased. So what we do for that, we update the W as W is equals to W, which is the old value, minus there is a learning rate, which is called the step size, multiplied with what is the gradient of my loss function with respect to that particular parameter. Gradient of my loss function with respect to that parameter. If it is known, then W is updated in the opposite direction of the gradient because we have a negative sign. That's why this is called gradient descent, because we are updating W in the opposite side of the gradient. That's why this is called the gradient descent approach. So in practice, we use the a mini batch gradient descent, where what we do, we take a batch of data. Batch of data means suppose if my data has 1 lakh number of images, but computationally we cannot, for example, suppose whatever my machine I have, I cannot process more than 256 images at one time. Then what I will do, I will take 256 as my batch size. From 1 lakh number of my training images, I will only take 256 random images, and then that I will refer as a batch of data and give as the input to my neural network. And then after that, I will get the loss and compute the gradient of my loss with respect to every parameter in the network. And then every parameter of the network is updated in the opposite direction of the gradient. Means weights is equals to weights minus the step size into the gradient that we have computed. That's how basically we apply the gradient descent here. So there is a question here. If problem is unsupervised, then how can we identify how many classes are there in classification? Okay, so for that, we need to perform the clustering. Suppose if you are performing the clustering, then how many number of clusters we are able to identify, that many number of classes we can assume. There is another question. Negative gradient means SIF. My slope is positive. It will update in the weight in the negative side. Yeah, exactly. That's what we want. We want to update in the opposite direction of the slope. Then only the loss will decrease, because if we update in the direction of the slope, then it will become the maximization problem. Then it will increase the loss, but our aim is to decrease the loss. That's why we update in the opposite direction. Okay, but what is the major question here is we need to find out the gradient here. We need to find out the gradient, because gradient is always required. So how we can compute the gradient? For that, we need to basically make use of the chain rule. And all of you are well aware with the chain rule. For example, suppose if we have a additive function x plus y, then del f by del x, which is the partial derivative with respect to x is 1, partial derivative with respect to y is 1. If we have a multiplicative function, partial derivative with respect to x is y, with respect to y is x. If we have a max function, then partial derivative with respect to that particular value, which is maximum is 1 and which is minimum is 0. So for example, del f by del x is 1 if x is greater than y, otherwise it is 0. Del f by del y is 1 if y is greater than x, otherwise it is 0. That's how we get the gradient here. So what happens here in neural network, because we have the multiple layers, then basically chain rule comes there, and using chain rule we compute. And I will skip this particular part right now, and I will take another example in a neural network, and then there I will basically show what is the meaning of that. So this computational graph I will skip right now because we have limited time left. I will show that using the equation form. So I will skip all these. This one we have already seen. Multi-layer neural network we have right now seen. Yeah. So now let's see here. Suppose we have the first layer, and first layer is written as f1 x comma w1. What is meaning of this? F1 means we are writing the first layer as a function. X is the input to that function. W1 is the parameter involved in this particular layer. And the output of this function is represented as h1, which is represented as the hidden representation h1. Now h1 will serve as the input to the next layer. Suppose next layer is written as f2 and its parameter is w2. So h1 is the input, w2 is parameter, its output is h2. So like that, even if we have the kth layer, then in kth layer, hk minus 1 will be the input, wk is the parameter in the kth layer, and hk is the output of this kth layer. That's how we can proceed. So that's how we can have a neural network. And what we need to do at the end, we need to add some loss function. So whatever is the output of the final layer, that is hk, is given as the input to a loss function L. And loss function also requires what is the ground truth class level of X. So the ground truth class level of X is Y. So that information is also given as the input. And that will basically gives us the final error value. And then we need to basically compute the gradient. Here for every parameter wk, we need to compute the gradient in order to update those parameters. For example, if wk is there in the kth layer, then and if we got the gradient of our error function with respect to that wk, which is represented as partial derivative of e with respect to this wk, that is the gradient here, that will get multiplied with the learning rate or the step size here. And then wk is updated in the opposite direction of the gradient. So that's what we need to do. What is very important here, how to find out this del E divided by del WK. That's what is very, very important. How to find out that. That's what we are going to understand. So, and basically we make use of the chain rule in order to do that. So what we do, now let's start with K is equals to 1. Suppose we have only one hidden layer. For example, we have only one layer here. So this F1 X comma W1, W1. And then its output is H1, which is given to the loss function, and we get the loss as the E. It means that this E can be represented as L of H1 comma Y, where H1 is the output of this F1. So H1 can be represented as H1 can be written as F1 X comma W1 comma Y. So that's what is my error function. So what we need to compute? Actually, we need to compute del E divided by del W1, but del E divided by del W1 we cannot directly compute, right? Because we have this hierarchy here. Then how we can compute del E divided by del W1? But we can compute del E divided by del H1 because E is equals to L of H1 comma Y, means E is a function of H1. Then we can directly compute del E divided by del H1. And we can also compute del H1 divided by del W1 because H1 is directly dependent upon W1. So we can compute del H1 divided by del W1. And we know in the calculus, the chain rule says that if we have del E divided by del H1, and if we also have del H1 divided by del W1, and if we multiply these two terms, then actually it is equivalent to finding del E divided by del H1. And that's what we wanted to find out. So what we wanted to find out, del E divided by del W1, and that we can find out as multiplication of del E divided by del H1 with del H1 divided by del W1. So here del E divided by del H1 is basically termed as the running gradient, or sometimes we say upstream gradient. This is the gradient which is being passed from one layer to another layer. What is del H1 divided by del W1? That is basically the gradient of that particular layer itself. That is called the local gradient. This is the local gradient of this layer. However, del E divided by del H1 is the upstream gradient, which is coming from the next layer. If we multiply both, then we get the gradient of final error function with respect to W1. Okay, now let's take one example here. Suppose if my function is defined as E is equals to y minus W1 transpose into x square. Suppose this is my error function where y is the class, where y is basically the ground truth. And this is not for classification. This might be for prediction, like age prediction problem. And what is this W1 transpose X? This W1 transpose X is actually the function F1. So the F1 is defined like this, W1 transpose X. So actually my error function is defined as Y minus whatever is the output of F function F1, that is H1. So Y minus H1 square. This is my error function where H1 is given as W1 transpose into X, which is basically the function F1. Okay, that's what is written here. So H1 is equals to F1 of X comma W1, which is nothing but W1 transpose X in this example. So error function is Y minus H1 square. Okay, what we need to compute if we want to update the parameters W1, what we need to compute del E divided by del W1. And we have already seen here using chain rule, del E divided by del W1 can be written as del E divided by del H1 multiplied with del H1 divided by del W1. Can we compute del E divided by del H1? Yes, we can compute because we know that E is equals to Y minus H1 square, then we can compute del E divided by del H1. Can we compute del H1 divided by del W1? Yes, we can compute because H1 is equals to W1 transpose X, then we can compute del H1 divided by del W1. And if we multiply both, then we get minus 2x times Y minus W1 transpose X. So that is basically the gradient that we get. How to update the parameter? So now W1 is equals to W1 minus learning rate multiplied with this del E divided by del W1. That's how basically we can compute it. So del H1, what is del H1 divided by del W1? Del H1 divided by del W1 is X itself because this is multiplication. This one is because there is a square also. So del E divided by del H1 is minus 2 times Y minus H1, and H1 is nothing but W1 transpose X. So it can be written as minus 2 times Y minus W1 transpose X. If you multiply both, we get this one, this term. Okay. Now, what happens if we have more layers? Suppose if k equals to 2. Now we have function f1, then we have function f2, and after that we have the loss. Then how? Then in that case, we need to find out del E divided by del W2 also. We need to find out del E divided by del W1 also. Now again, let's take the example. Then what will happen? Now we have del first, what is the first thing that we compute? Del E divided by del H2. Then we compute del H2 divided by del W2. And if we have del H2 divided by del W2, then we can find out del E divided by del W2. Because del E divided by del W2 is nothing but upstream gradient, which is del E divided by del H2 multiplied with del H2 divided by del W2, which is the local gradient. That's how we can get with respect to W2. But we need to also find out del E divided by del W1. So now using chain rule, we can have this del E divided by del 1, del E divided by del W1 can be represented as del E divided by del H2 into del H2 divided by del H1 into del H1 divided by del W1. So that's what basically we can write. So ultimately, what we need to compute? We need to compute the gradient of error function with respect to W1. But we cannot compute directly. But using chain rule, del E divided by del W1 can be computed as del E divided by del H2, which is the upstream gradient here, multiplied with the local gradient of H2 with respect to H1, which is del H2 divided by del H1, that we can compute, into what is the local gradient of H1 with respect to W1, that is del H1 divided by del W1. So using chain rule, what happens? This del H2 cancelled out, del H1 cancelled out. So what remains is del E divided by del W1. Again, let's take one example. Suppose now my error function is defined as E is equals to minus log of, so this is basically minus log means cross entropy loss. So we use the cross entropy loss, and this sigmoid, this one is sigmoid here, this sigma is sigmoid of W1 transpose X. So basically now we have W1 transpose X is basically this first F1, sigmoid is F2, minus log is basically my error function here that we take. And let's assume the value of y is 1, because this is again the classification problem. Then we need to find out these values. So how to find out? So H1 is equals to W1 transpose X, H2 is equals to sigmoid of H1 itself, because this is F2, and E is equals to L of H2 comma 1, which is given as minus log of H2. What we need to compute? We need to compute del E divided by del W1. So del E divided by del W1, how it can be computed? Del E divided by del H2 into del H2 divided by del H1 plus into del H1 divided by del W1. So can we get all these independently? Yes. What is del E divided by del H2? So E is equals to minus log of H2. So we can compute del E divided by del H2. Can we compute del H1 divided by del W1? Yes, we can compute, that is X itself. Can we compute del H2 divided by del H1? We can compute, because this is sigmoid function. So basically del H1 divided by del W1 will be X itself. Del H2 divided by del H1 is basically sigmoid of H1 into 1 minus sigmoid of H1. Del E divided by del H2, because this is minus log, so this is minus 1 divided by H2. We can replace all H1 with W1 transpose X. We can replace all H2 as sigmoid of H1 and then replace H1 with W transpose X. So that's how basically after replacing everything, we can get the final del E divided by del W1, which after solving, which is written as minus sigmoid of minus W1 transpose X into X. That's how basically we can compute using chain rule. So even if we have even if we have the jth in jth layer means Wj, then how we can compute del E divided by del Wj? So that is del E divided by del Hk into del Hk divided by del Hk minus 1 into del Hk 1 minus divided by del Hk minus 2 dot up to del Hj plus 1 divided by del Hj and then del Hj divided by del Wj. So that's how basically even we can compute in general case. And this is basically called the backpropagation. What is backpropagation? So basically what happens when we are updating Wk, then by that time we would have computed del E divided by del Hk. When we are going to compute for Wk minus 1, by that time we would have computed this del E divided by del Hk into del Hk divided by del Hk minus 1. The same thing will be passed here to the previous layer, and del Hk minus 1 divided by del Hk minus 2 will be multiplied there and passed to the previous layer again. That's what is called the backpropagation. Basically, this upstream gradient, we would be simply backpropagating from the final layer to the first layer. And then whatever is the local gradient to that particular layer, which is del Hj divided by del Wj, will be multiplied in that upstream gradient. And that will basically become the final gradient to be utilized for updating the parameter in any given layer. Like that. So this is the upstream gradient in this case. This is the local gradient of this gth layer. And then finally, this is passed. Okay, so in summary, what we have in any given layer, we have its parameter Wk. We are receiving some input from the previous layer, which is Hk minus 1. And we perform some computation here and generate the output Hk to be passed to the next layer. So this is the forward pass. During backward pass, what happens? We receive the upstream gradient, which is del E divided by del Hk that we are receiving as the input during backpropagation. What we compute? We compute two local gradient. One local gradient is gradient of Hk with respect to Wk. That will be used to update the parameters of Wk. We also compute the local gradient of Hk with respect to Hk minus 1. That will be used to compute the upstream gradient, this downstream gradient to be passed to the previous layer. So we compute the local gradient Hk with respect to Wk and Hk with respect to Wk minus 1. So if we multiply del Hk divided by del Wk in this upstream gradient, then we get the gradient which is required for the parameter update. But if we multiply del hk divided by del hk minus 1 into this del E divided by del hk, then we get the downstream gradient, which is going to be passed to the previous layer. So that's how basically this entire forward pass and backward pass to a particular layer is working. Sometimes it is also possible that we can have a very complex computational graph where multiple inputs are coming, multiple outputs are there. Then in that case, what can be done? Suppose if we receive multiple inputs and also we are having multiple outputs as well, then what happens during forward pass, when we are having multiple outputs, then exactly same thing is copied in all the branches. For example, whatever output we get, same output is passed here also and same output is passed here also. Or if we have a different function, then based on that function, it will be computed. However, when we are performing the backpropagation, then what happens? The upstream gradient that we receive from one branch and other branch, both are simply added, and that will be considered as the final upstream gradient to be utilized for this rest of the process. Okay, so now if you see, if you are training any multi-layer neural network, so in general, what is happening? We have the neural network. We first do the forward pass. In forward pass, we give our input, and then in every layer, we compute these features, which is this edge, the hidden representation edge, which is going to be which will serve as the input to the next layer. Like that, we keep computing. At the end, we have the classifier that finally gives us the loss function. And when we get the final loss function, then during back propagation, we start computing the gradient for our error function with respect to every parameter in the network in every layer. And once we get the gradient, then after that, every parameter is updated using that gradient as W is equals to W minus learning rate multiplied with gradient of error function or the loss function with respect to that parameter. And this process we repeat multiple times. Once our training process is finished, means the error that we are getting is saturated, then we stop the training and then our model is finally trained. Okay, so far, if there is any question, we can take it up. Okay, so there is a question, what if we get stuck somewhere like local minima? Yeah, this is very common problem. We can get stuck in local minima. So for that, there are the other variants of optimizers, like we have SGD with momentum, we have Adam optimizer. Those optimizers are able to solve this problem. How? That we will see. In batch ZD, each batch is processed for the number of epochs. Yes. So what happens here? Suppose if we have 10,000, suppose if we have 1,000 number of samples, and if my batch size is 100, then we have 10 batches. So we first feed first one batch, then second batch, then third batch, fourth batch, fifth batch. So all the batches first we feed one by one. Then that is basically the completion of one epoch of training. After that, we repeat the same thing. Again, we take the first batch, then second batch, then third batch. Again, we take all the batches one by one. That completes the second epoch. Then again, we start. Then we take the third epoch, fourth epoch, like that. What is hyperparameter? Hyperparameter is something that we are setting. For example, how many number of neurons are there that we are setting? That is the hyperparameter. And which activation function we are using, that we are setting, that is the hyperparameter. So anything that we are setting is the hyperparameter. Anything which is learned by the network, that is the parameter. How did we find H1? H1 was computed using function F1. So F1 was W1 transpose X. So W1 transpose X was H1. We got this, but missed what you said. This is not a classification problem, but it is case representation. Could you explain? Okay, that problem which I discussed there, because that loss function was y minus W1 transpose X square. So basically that was a kind of a regression problem, that there we wanted W1 transpose X to come closer to y. So that was not a classification problem, rather it was a regression problem. However, the second case where I have taken minus log of sigmoid of W transpose X, that was a classification problem, because there we considered the class label as 1 for the given input and we wanted the probability for that class to be towards 1. That's why we use minus log of this function cross entropy. Why is H2 is equals to F2 H1? Because we have the because F1 is my first hidden layer, F2 is my second hidden layer. So the output of the first hidden layer will become the input for the second hidden layer, and output of first hidden layer is H1. That will become the input for the second hidden layer. So F2 will take H1 as the input, and it will produce H2 as the output. While coding this, there won't be any variables and only numbers in place of EWS. So won't the gradient come zero as all are constant? I mean, how will it identify the local function? Okay, so usually what happens whenever you are setting your problem in PyTorch, TensorFlow, and even Keras and all these platforms, usually you don't have to bother about computation of the gradients and all these things because it is already inbuilt there. What you have to do there, you have to only set up your layers, and you have to just see the proper connectivity that the output of the first layer is given as the input to the second layer, output of the second layer is given as the input to the third layer, and rest of the things of computation of this gradient and all is already taken care by the optimizers. For example, if you are using Atom optimizer, then Atom optimizer will do that task for you. It will basically compute all the gradients and perform the updates accordingly. So you need not to bother there. But conceptually, you should be able to know that how this is happening. Please tell upstream gradient and local gradient difference. So upstream gradient is the gradient computed so far. That is basically the product of the all gradients that we computed, right? And what is local gradient is gradient for the current layer itself. For example, suppose if I have 4 hidden layers, and if I am right now computing gradient in the first hidden layer, then we would have computed in the last layer, then second last layer, in the third last layer, and then we would have multiplied and back propagated. That is actually the upstream gradient. And the gradient that we compute only for the current layer is the local gradient. The final gradient is used to update each and every weight or just the weights of a particular hidden layer. No, for every parameter in every hidden layer, we compute the gradient and we update every parameter in every hidden layer. So all the parameters will be updated. Even if there is a bias term, then we compute gradient for bias term also and update that bias term as well. Weights and biases are parameters of network and input X, and all the intermediate outputs are features. Are there any other parameters and features? Okay, other parameters may be there that suppose if we use some other type of layers, for example, if someone uses batch normalization layer, so there also might be parameters. Or if you are designing your own layer for any purpose, that might also have the parameters. So that depends. Suppose if someone is using dropout, there is no parameter, but dropout will also transform the features, means that acts as a regularizer. So what if you are using, suppose if someone is using pooling, max pooling layer, that is also one of the layer. So there is also no parameter, but your features will be transformed. We feed numbers to the system. Then how do I understand in terms of vector and make a meaningful differentiation? So actually we feed the vector itself. For example, if I'm feeding my input data, so my input data is represented in d-dimensional feature vector, and that's what we are giving as the input. And because we are giving, suppose if there are d number of values for my one sample, then all these d values will serve as the input. And then my first layer will also have, will have suppose k number of neurons. Then every neuron will also have d number of parameters. And then every value of my input will get multiplied with the corresponding w values. And then that's how we perform this w dot x plus b. There is another question. Could you give an example of vanishing gradient in the network as the signal back propagates? Okay, so what happens here? Suppose we have the suppose we have the sigmoid activation function, for example. Then what happens when the value of x is 10? When the value of x is 10, then for that particular value of x is 10, if you compute the gradient will be close to 0. If gradient is close, suppose if your local gradient is close to 0, your upstream gradient is going to be multiplied with the local gradient and then passed to the previous layer. And whatever upstream gradient you have, but the local gradient, if it is close to zero, then entire upstream gradient itself will become close to zero. And that's what we would be passing to the previous layers. So it means that the gradient information is going to be diminished due to the multiplication by the local gradient, which is close to zero. And why it is close to zero? Because the function in that local, the whatever local layer right now we have, that function is basically having the saturation. It's kind of a means the flat curve that we have. For example, if you see the sigmoid, so sigmoid is like this. So if you are having 10, this is a flat area where the gradient is close to zero. Or minus 10, gradient is close to zero. So that's how basically it will suffer with the vanishing gradient problem. In case of CNN, learning is done in the neural network. Convolutional layers only feature extraction is done. No, convolution layer also has the parameters. So convolution layer also has the parameters. So learning is actually happening in the convolution layer as well. And there is the fully connected layer. The normal neural network layers are only at the end of the convolution neural network. You do not have in between. So initially you only have the convolution layers, max pooling layers, non-linearity layers. At the end only you have the fully connected layers there. But either it is convolution layer or fully connected layer, both has the parameters, both will be learned. There is another question. Suppose we want to use this kind of a structure to predict age Y of a person from input features of face image. Will we have to feed the actual Y values to compute the loss? Okay, you don't have to feed the actual Y value to the network to compute the loss. You have to feed actual Y value only to the loss function to compute the loss. For example, suppose if my age is 37, but my neural network has predicted 40. So now 40 minus 37 square, that's what will become the L2 loss in this particular case. Another question is, what is downstream gradient? Gradient that we are passing to the previous layer is downstream gradient. Gradient that we are receiving from the next layer is the upstream gradient. So that is the difference in upstream gradient and downstream gradient. What is batch normalization? So batch normalization is actually used to perform the regularization. Sometimes what happens, our data distribution doesn't follow the Gaussian. And when it doesn't follow the Gaussian, then optimization becomes an issue. So in order to get rid of that problem, batch normalization is there. So in regularization topic, you will be able to get this particular term, batch normalization. There you will be able to get better clarity. How to overcome, another question is how to overcome the problem of gradient skipping or vanishing gradients at any local level of the neuron itself. There are several approaches for that. For example, we can have the residual connection, which is done by the ResNet. We can have the auxiliary classification layers, which is done by the GoogleNet. And even there are many more. And even we can have we can design a better nonlinear function, which is free of the vanishing gradient problem, or we can, all the layers that we are using is free of the vanishing gradient problem. So there are several approaches which can be adopted in order to ensure that this gradient vanishing problem is not occurring. Okay, so even I wanted to cover different variants of the optimizers like SGD with momentum and this Adam and all these. But I think due to the time limited and a lot of queries that came, now it is not possible to cover those topics. Maybe in any other session you will come to know. But what is the basic stochastic gradients? What is the gradient descent approach and how this is useful to train the model? I hope you would have got the idea. The rest of the variants that we have here is only some minor modifications in the approaches to ensure that what are the major problems with the normal SGD, which is actually tackled in other variants of the optimizers. Is one of the problem is it is also possible that lot of zigzag jitterness is happening in one dimension, which can be reduced. There could be a problem of local minima or saddle point where gradient is zero. We can get stuck there using SGD. It means stochastic gradient descent. So this problem is actually tackled. And because we perform the updates using the mini batch, so every time the samples that comes in a batch of data might be completely different as compared to other batch of data. So that also creates a problem. Sometimes it basically gives us the diversion in case of the optimization trajectory. So this kind of a noise that it creates in the optimization trajectory. So these three are the major problems. And one other problem is oscillation near minima, when we are actually near minima, but we are oscillating there. That happens due to the this gradient that we have. And that is very common problem in ADAM. So all these are the problems, and other optimizers try to resolve these problems. And now I think due to the time limit, we are not able to go in that part. We will see if possible in some other session to cover this. So there is some question again here, when to go for transfer learning models rather than CNN. Transfer learning can be done in CNN also. Transfer learning is a completely different concept. CNN is a different concept. Transfer learning can be applied in any neural network. Either it is CNN or just ANN, or even it is GAN, or even you have RNN. Anywhere you can use the transfer learning. Transfer learning means you already have a trained model on a larger data set. Transfer that knowledge to your to the model that you are going to use for your some small scale data set, because at the end they have similar basic level characteristic. For example, even suppose if you have a very large scale data set of different objects, if you have a small scale data set, still their basic features like line, corners, all these things will be similar. So we can utilize the already trained model for that purpose. We can only fine tune some last layers, because last layers basically transform the final feature into very abstract way. So there it is, the later layer features are very, very dependent upon the problem we are solving. But early layer features are very, very basic or primitive features. So in transfer learning, we retain the basic and primitive features as it is, but fine tune the abstract features, which is the task specific features, and which is towards the end of the network. What is convex optimization? Convex optimization is very simple. For example, if you have y is equals to x squared, this type of plot where your global minima is guaranteed is basically the convex optimization, where you have only one minima and that is the global minima. That is the convex. And what is non-convex? Where you have multiple, where you have a lot of local minimas. That is basically the non-convex problem. In practice, the deep learning optimization that we are doing is non-convex optimization problem. Another question is, suppose our data is in the form of 0 and 1, and we want to compute only where there is 1. So how can we model the event is 1? So how can we model the event 1 such that we do not get into gradient skipping calculations while back propagating like it have? Your question is not clear. Can you elaborate your question? Another question is, are you going to cover CNNs in detail in another session? Yes, CNN we will cover in some other session. Difference between transfer learning and knowledge distillation. Okay. In case of the transfer learning, we make use of the same network fine-tuned on other data set. But in knowledge distillation, we make use of some other network and transfer the knowledge from one already trained network to some other non-trained, untrained network. But in transfer learning, the same trained network is going to be fine-tuned on some other data set. That's what is the basic difference. Another question is, oscillation can be minimized by keeping the LR very low, right? Because yes, that can be done. But if your LR is very low, then that creates the problem that you will not be able to reach to the minima itself. But once you reach to the minima, then only you can have the LR very low. And that's what is the practice that people follow. Initially, learning rate is high, but while you are training the models, after some number of iterations, your learning rate is decreased. Even multiple times it is decreased. What I think that LR discretizes the moves towards the minima. So the lower the LR is, more smoother moves will be towards minima and hence avoiding the oscillation. Yes, that is possible. But if your LR is not properly chosen, then you will end up in the this convergence problem. Then your model will not be converged at all. What is autoencoder? Another question is, what is autoencoder? So autoencoder is basically, now we can think of a two neural network. One neural network converts data into feature. Another neural network try to convert that feature into data again. Means converting data to the feature, then feature to the data using two network. Then one neural network which converts data to the feature is called encoder. The network which convert feature to data is called decoder. Suppose if I have an image, a cat image. Now encoder will convert that cat image into a feature vector of some dimensionality. Now decoder will convert that feature vector again into the cat image. So what was the original cat image and what is the predicted cat image? Now we wanted to minimize the difference between them. And that's what will basically become my error function in autoencoder. Okay, so there is a other question here is in SNN, we use impulses for the presence of an event. While training SNN, we use either ANN to SNN conversion method, while compromises accuracy to another method is to use backpropagation using surrogate gradients. But in this method, some of the gradient are skipped due to non-differentiable nature of spikes. Yes, so we use 8 10H, but still training SNN is difficult. So how to overcome this situation so that training is done without skipping? Okay, so if there are some functions that you are using which are not differentiable, then it is not possible to do without skipping. The only way can be done is any function which is non-differentiable but used in your network during backpropagation, instead of using backpropagation for that non-differentiable function, you can take some approximated function of that function which is differentiable, and backpropagation can be done via that differentiable approximated function instead of original non-differentiable function. So that's what can be done. And this is being done in one of the problem in image retrieval also, because in image retrieval we want to find out the similar images. So there are also non-differentiable properties there, because we want to perform the hashing. We want to convert my feature vector into a binary pattern of 0 and 1, and because in this hashing is not this hashing is non-differentiable. So, but at the time of back propagation, that hashing, which is just binary conversion, is actually approximated using the sigmoid, and back propagation actually happens through the sigmoid instead of just the sine function converting 0 and 1. Okay, so I think now we can stop. Maybe further questions we can take in some other session, or even you can write to me. Then I will try to answer your questions. So my email ID is srdube@IIITA.ac.in. Okay, so thank you very much to all the participants for attending this session and having a lot of interactions here, a lot of questions. So, and due to that, I was not able to cover these different optimizers, but at least we have covered the basic concepts, the idea that you have got. Then you will be able to, even by own, also if you just see the different variants of the optimizers, quickly you can understand.
Thank you, sir. Thank you so much for such a detailed session. Your clear explanations and practical insights are very valuable to us and greatly appreciated by all of us. Thank you very much. Thank you very much for joining us.
Thank you. Thank you very much to all the participants and Dr. Rakesh also, and everyone present here.